Hello, my name is Minghan Li, and I am presenting TurnAhead, designing 3 degrees of freedom rotational haptic cues to improve first-person viewing experiences. This research was conducted in collaboration with co-authors Bo-Cheng, Chen, Chia-Yu, Chiao-Ju, Yun-Fang Li, Shun-Yu Wang, Fang, and our research advisor, Mike and Chen. First-person viewing drones, or FPV drones, provide accurate piloting and thrilling visual perspectives. As these drones become more popular, FPV footage gradually becomes one of the shooting ways in movies, commercials, and social media. Furthermore, with the advancement of VR technology, people can now experience more immersive viewing of FPV videos through VR headsets. However, the motion of the camera, particularly rotation, can create visual discomfort due to the inconsistency between the perceived visual motion and the vestibular motion. We present TurnAhead, which provides haptic feedback before the camera rotation in an FPV video. It uses headset-mounted air jets to provide ungrounded rotational forces corresponding to camera rotation in 3 axes: pitch, roll, and yaw. We would first go through a top FPV video analysis that would be essential to our following system design process. We collected the 30 most popular FPV videos from YouTube and Airviews, a top video sharing site specifically for drone videos. We manually analyzed these videos by rotational speed, angle, axis, and time duration. We categorized these rotations into single axis, 2 axis, and 3 axis, and scoped the rotational time distribution. We discovered that the most common rotational axis is yaw, with 84% of all rotations having yaw as one of their rotational axes. Furthermore, these charts show the cumulative distribution of the rotational speed and angle, measured along the 3 axes. We will use these results in our follow-up design process. For example, we choose the 90th and 10th percentile values as the upper bound and lower bound of rotational speed and angle. The previous head-mounted haptic systems could create ungrounded 1-DoF and 2-DoF translational force feedback in several ways, including shifting torques provided by motors, air propulsion, and electrical muscle stimulation. However, all these devices could not support the FPV viewing experience for its 3-DoF translational and rotational feedback. Air-based solutions, such as air jets and propellers, have the potential for portable functionality and instant force feedback among all power sources. Eventually, due to the lower latency, lighter weight, and lower noise compared to propellers, we selected air jets for TurnAhead. We will now discuss how TurnAhead works. The system has 2 main components: a pneumatic control system for the power supply, and 6 nozzles mounted on 3D printed headsets. The pneumatic control system has 3 pressure regulators, 6 solenoid valves, and PCB to control the force magnitude and propulsion direction. The nozzle positions have been organized to provide rotational cues for each axis. However, when there is multi-axis rotation, we face 2 types of nozzle conflicts. When 2 rotations require the same nozzle, we would use force addition to optimize nozzle usage. On the other hand, when opposing nozzles are activated at the same time, we would use force subtraction to address it. Moreover, we have open-sourced the entire system, including the 3D models of nozzle mounties, electronic layout, and control system written using Arduino code and C#. We will now discuss the user studies part of our research. First, we want to determine the minimum duration and intensity of haptic cues that users could perceive and recognize accurately. These statistics could assure the effectiveness of the haptic cue. To do this, we used the constant stimuli method from psychophysical studies. We chose 5 different torque intensities and durations, and combined them with 6 rotational directions to create 150 conditions. Participants will perceive haptic cues without any visual feedback and be asked to verbally identify the direction they felt or say unknown if they were unsure. The following line charts display the percentage of participants who correctly identified the direction of the haptic cue. The horizontal axis represents the time duration, and the vertical axis represents the ratio of correct responses. The different line colors represent varying torque intensities, with darker lines indicating stronger torque. We can observe several patterns. First, the accuracy percentage increases as the time duration and torque strength increase. Second, the accuracy is balanced for each axis. For instance, the left and right directions of the yaw has similar accuracy. Lastly, the accuracy for the roll axis is significantly lower than the pitch and yaw. We set 75% correct performance as the recognition threshold of the haptic cue's intensity. We chose 250 milliseconds as a minimum duration standard since the accuracy for the roll axis would not exceed 75% until 250 millisecond duration. As a result, for at least 75% of participants to correctly recognize all cue directions, it requires torque values of 4 Newton-centimeter in pitch and yaw directions and 8 Newton-centimeter in the roll direction. These torque values will be the minimum recognition threshold in the later haptic cue designs. Next, we like to improve the viewing experience by designing a haptic pattern regarding rotational speed and progress. To enable users to recognize different rotational speeds more comfortably, we developed a scaled mapping model, which is shown on the right, to scale the feedback intensity linearly with the rotational speed. Participants were asked to evaluate two paths, one using a constant and the other using a scaled torque haptic design. The results indicate an equal preference for both designs and only a slight difference regarding comfort and immersion. Despite the similar performance of both designs, based on the feedback we received, we eventually selected the scaled design for TurnAhead. We also found that there was no way to expect when the rotation would stop, and it was uncomfortable to push the head during the rotation continuously. To address it, we developed an ease-out force pattern with gradually decreasing force strength from the beginning to the end of a camera rotation. Similar to a previous phase of the study, the participants were asked to evaluate two paths, one using fixed force to the end of the rotation and the other using an ease-out design. The result shows that the ease-out design was preferred regarding predictability, comfort, and immersion, so we selected the ease-out design for TurnAhead. Next comes the anticipatory timing study. In this study, we want to know whether the experience would be more comfortable if we could anticipate the future path. Inspired by prior research, which found that drivers experience less motion sickness than passengers due to their ability to anticipate turns, we developed anticipatory cue designs that provide users cues before the view rotation. The gray section represents the actual rotation viewed by users, while the blue section represents an anticipatory cue before the turn. The anticipatory timing should surpass the 250 millisecond recognition threshold identified in a previous study to ensure users have sufficient time to recognize the upcoming rotation. We have selected 3 timing options to explore: 300, 600, and 900 milliseconds. Participants experienced 3 paths with different anticipatory time durations, and we collected feedback on predictability, comfort, immersion, and overall experience. Based on the analysis of statistics and feedback, we concluded that a 300 millisecond anticipatory time was barely noticeable, while 900 milliseconds seemed to be too long for some participants. Therefore, we decided to use a 600 millisecond anticipatory timing for the evaluation study. In the user experience evaluation, we opt to know whether TurnAhead could improve the FPV viewing experience and which haptic design is better. To evaluate it, we conducted a user study comparing 3 conditions: anticipatory cue, onset cue, and no cue, which is the baseline condition. We created 3 scenarios to cover different FPV content types. The first scenario involves 3 paths in a VR environment with indoor and outdoor scenes. The second and third scenarios are 3 2D videos selected from popular indoor and outdoor FPV footage. The result shows the average comfort, immersion, and enjoyment ratings on a 7-point Likert scale and overall preference across all 3 scenarios. In general, the participants rated both time designs of TurnAhead to have significantly higher comfort, immersion, and enjoyment than the baseline. In terms of overall preference, 89% of the participants preferred TurnAhead, and among them, the timing preference was split to 52% preferring anticipatory and 48% preferring onset. This result indicates an even preference for anticipatory and onset cues. Feedback showed that anticipatory cues improve predictability and are suitable for relaxing and cinematic content. In contrast, an exciting segment that involves instant rotation above cities could match the onset cues for better synchronization of vestibular and visual perception and more excitement. We intend to investigate the impact of combining and varying time to understand how it influences the user experience. This is the end of the presentation. Thank you for listening.